All right, good afternoon. Today is Monday the 10th. We're going to get ready to move on with our bell ringer, and then we'll move into a short video and have some direct instruction on the electromagnetic spectrum. Everything that we're going to cover today and tomorrow and Wednesday will be on your quiz. So your next quiz is scheduled for this Thursday. That will be your last quiz of fourth quarter. So quiz 4 will be on Thursday the 13th. So I'm going to post a message in the chat so that you guys know that. All right. So on the 13th, you will have your next quiz. That'll be quiz 4, the last quiz of this quarter. All right. So let's take a look at this bell ringer. We haven't talked too much in detail about this, but this is looking at reflection. At this point, you guys should know that light waves reflect. All waves, actually, not just light waves, but all waves in general do reflect. So let's kind of take a look at this here. It says, which picture shows how a mirror reflects light? I'm just going to take a look at what some of you guys posted. So the correct answer for this one is, in fact, B. So let's take a look and work through each of these options. So letter A, here's our flashlight, here's our surface, and there's a light shining on it. But clearly, A is showing that this is, well, a transparent object, meaning that light would pass through it. But we know that the question is asking you about a mirror reflecting light, so we can eliminate option A. We already know B is the answer, but let's take a look at C and D. C shows that the light beams are being reflected, but when you look at something or you shine a light on it, the reflective light or the reflected waves don't bounce back parallel to the original. Also in letter D, it shows that it is being reflected at a direct 90-degree angle, and that's not the case. In fact, B is the correct response because in the law of reflection states that if a light is applied at an angle, then the reflective angle is usually somewhere around 60 degrees. And so if you had a protractor to measure that, that's what you would come out with. So light reflects from a reflective surface at around a 60-degree angle from what we call the angle of incident, meaning where the original light waves interact with the surface. So the answer here is B, and we will talk more about that, reflectance, refraction, absorption, all that stuff in the next few days. All right. Okay, so before we get into direct instruction, I want to show you guys a little bit of a video just to get you thinking about light waves. Remember last week we covered waves in general. We talked about the fact that the electromagnetic spectrum does not require a medium to travel through. So unlike sound or other waves, it can travel through empty space or in a vacuum, and it does just that. So that's why radio waves and things like that are able to go through space, essentially. That's why humans are able to communicate with instruments that we send off into space. So every time those probes or satellites are sent off to orbit other planets, we can receive signals back or send a signal to those probes. That's also why we're able to communicate with people on the International Space Station, because the electromagnetic spectrum that we use, or these EM waves that we use to transmit information, can go through the vacuum of space, and they can penetrate, some of them can penetrate our Earth's atmosphere. All right, so let's take a look. Let me make sure my settings are good to go, and we're going to watch a brief video, and then we'll get started on our direct instruction.
What if you could only see one color? Imagine, for instance, that you could only see things that were red, and that everything else was completely invisible to you. As it turns out, that's how you live your life all the time, because your eyes can only see a minuscule part of the full spectrum of light. Different kinds of light are all around you every day, but are invisible to the human eye. From the radio waves that carry your favorite songs, to the X-rays doctors use to see inside of you, to the microwaves that heat up your food. In order to understand how these can all be light, we'll need to know a thing or two about what light is. Light is electromagnetic radiation that acts like both a wave and a particle. Light waves are kind of like waves on the ocean. There are big waves and small waves, waves that crash on the shore one right after the other, and waves that only roll in every so often. The size of a wave is called its wavelength, and how often it comes by is called its frequency. Imagine being a boat in that ocean, bobbing up and down as the waves go by. If the waves that day have long wavelengths, they'll make you bob only so often, or at a low frequency. If the waves instead have short wavelengths, they'll be close together and you'll bob up and down much more often, at a high frequency. Different kinds of light are all waves, they just have different wavelengths and frequencies. If you know the wavelength or frequency of a wave of light, you can also figure out its energy. Long wavelengths have low energies, while short wavelengths have high energies. It's easy to remember if you think about being in that boat. If you were out sailing on a day with short, choppy waves, you'd probably be pretty high energy yourself, running around to keep things from falling over. But on a long wavelength sea, you'd be rolling along, relaxed, low energy. The energy of light tells us how it will interact with matter, for example, the cells of our eyes. When we see, it's because the energy of light stimulates a receptor in our eye called the retina. Our retina are only sensitive to light with a very small range in energy, and so we call that range of light visible light. Inside our retina are special receptors called rods and cones. The rods measure brightness, so we know how much light there is. The cones are in charge of what color of light we see, because different cones are sensitive to different energies of light. Some cones are more excited by light that is long wavelength and low energy, and other cones are more excited by short wavelength, high energy light. When light hits our eye, the relative amount of energy each cone measures signals our brain to perceive colors. The rainbow we perceive is actually visible light in order of its energy. At one side of the rainbow is low energy light, we see as red, and at the other side is high energy light, we see as blue. If light shines on us that has an energy our retina can't measure, we won't be able to see it. Light that is too short wavelength or high energy gets absorbed by the eye's surface before it can even get to the retina, and light that is too long wavelength doesn't have enough energy to stimulate our retina at all. The only thing that makes one kind of light different from another is its wavelength. Radio waves have long wavelengths, while X-rays have short wavelengths, and visible light, the kind you can actually see, is somewhere in between. Even though our eyes can't detect light outside of the visible range, we can build special detectors that are stimulated by these other wavelengths of light, kind of like digital eyes. With these devices, we can measure the light that is there, even though we can't see it ourselves. So take a step back and think about all of this for a moment. Even though they seem different, the warmth you feel from a crackling fire is the same as the sun shining on you on a beautiful day. The same as ultraviolet light you put on sunscreen to protect yourself from, the same thing as your TV, your radio, and your microwave. Now those examples are all things here on Earth, things you experience in your everyday life. But here's something even more amazing. Our universe gives off the full spectrum of light too. When you think of the night sky, you probably think of being able to see the stars shining with your own eyes. But that's just visible light, which you now know is only a tiny part of the full spectrum. If we had to draw the universe and could only use visible light, it'd be like having only one crayon. Pretty sad. To see the universe in its full spectrum, we need to have the right eyes. And that means using special telescopes that can help us see beyond visible light. You've probably heard of the Hubble Space Telescope and seen its beautiful pictures taken in visible and ultraviolet light. But you might not know that there are almost 20 space telescopes in orbit, missions that can each see part of the full spectrum of light. With telescopes acting as our virtual eyes, both in space and here on Earth, we can see some amazing things. And the coolest thing of all? No matter the wavelength or energy, the light that we see out in the distant universe is the same thing as the light that we can experience and study here on Earth. So since we know the physics of how X-ray, ultraviolet light, or microwaves work here, We can study the light of a distant star or galaxy and know what kinds of things are happening there too. So as you go about your daily life, think beyond what your eyes can and can't see. Knowing just a little bit about the natural world can help you perceive the full spectrum around you all the time.
All right, so hopefully you guys found that interesting, just kind of an introduction to the different parts of the EM spectrum. We kind of touched on this last week, but that's kind of our focus for the next few days. We're going to talk about different components of the EM spectrum, what they're used for, why they matter, are they harmful, are they not harmful? And then as the week goes on into next week, we'll actually move into talking more about sound waves. So the next step in what we're going to be doing today is I'm going to go through some direct instruction, and after I am done, you guys will go back into the Google Doc posted here and you will submit your fill in the blank notes. So when you click on the tab that says virtual or absent students only, there's two things here. Here's your PDF if you want to go back and take a look. And then there's also some notes all about EM notes outline. So when you click on that, you'll see it's going to open up with some blanks here. You guys are just going to fill these in and post when we are done. So there's two segments here, the electromagnetic spectrum and then the spectrum of waves. Fill them in and post it. So now let's take a look at some information on the electromagnetic spectrum just to take things a step further. Tomorrow, you will be doing a virtual lab where you observe the behavior of different compounds when they are exposed to different sections of the electromagnetic spectrum. Okay, so here we are, the electromagnetic spectrum, or simply EM spectrum. You'll see it abbreviated as EM on a lot of your notes or on worksheets and things like that. But here's kind of a generalized example. So notice it shows you the first thing at the top is the wavelength. So within the EM spectrum, even though these are not mechanical waves, meaning they can travel through open space or in a vacuum. They don't have to have matter to travel through. The waves themselves still take on the pattern of a transverse wave, and we'll see that as we move through the next few slides. So the difference here between the different sections of the EM spectrum is actually based off of the wavelength. So yes, different waves change speed or amplitude, but in this case, the specific difference between these components are just the wavelength. Some are shorter and some are longer. And the difference between the wavelengths will also correspond to the amount of energy. But hopefully you guys can see here, not only do they show you the wavelength, but also gives you a visual of the size of the wavelength. As you move across here, some are very large and some are very small. So for example, here, some of the larger ones are about the size of a large soccer field or a house, some of the size of a baseball, and then you just kind of keep moving down, 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 and they become smaller and smaller. It also gives you an example of different waves that kind of fall within here, and also some sources. How are they generated, especially by humans? How do we generate some of these? So for example, a light bulb here, radiation or radioactive decay is down here. So these are all kind of different examples. So again, the EM spectrum is the entire range of EM waves in order of increasing frequency and decreasing wavelength. As you go from left to right, the wavelength gets smaller and the frequencies get higher. This is an inverse relationship between the wave size and frequency. And we talked about this last week when we looked at waves. The longer the wavelength or the larger the wavelength, the smaller the frequency. So it's inverse because as one goes up, the other goes down. The speed of all EM waves is the speed of light. This is a key fact for you guys to take away from this. There is different energy being carried between these, and there are different frequencies and wavelengths. However, all of these waves travel at the same speed. And that's about 300,000 kilometers per second, which is the speed of light. So they all have the same speed. They just have different wavelengths, frequencies, and different energies associated with them. So some key points for you to remember about the EM spectrum and about waves in general. The higher the frequency, the more energy they have. So the more of those little up and down troughs and crests, the more energy they have. They do not require a medium to travel through, so they can travel through the empty vacuum of space. They are also considered to be transverse waves. And I mentioned this earlier, and that's because they are vibrating electrical and magnetic fields at right angles to each other in the direction the waves are traveling. So they will have crests and troughs similar to what we observed in mechanical transverse waves. And lastly, there is an inverse relationship between wave size and frequency. So as the wavelength gets smaller, frequencies get higher. So let's talk about them in their order of wavelength, basically. Which one has the largest? So we're going to start with the largest wavelength and move down the list to the smallest. So the largest wavelength are radio waves. They have the longest wavelength and lowest frequencies. Some of them are as large as 1,000 meters. Some less than a meter, some about a meter in length. So what I want you to remember is that wavelength is the distance between two crests or two troughs. So this is the space that exists between the top curves of these waves. So radio waves are huge, some the size of a house, very, very large. And how are they important? Well, all different types of waves, right? Satellite transmission, radars, listening to the radio, basic radio waves in your car. All of those are examples. What about infrared waves? They come next. They have a shorter wavelength, and they do have a higher frequency when compared to radio waves. They can be used for finding people in the dark, also in TV remote controls. So if you have your TV remote, right, you point at the TV, press the power button, volume, whatever, well, how does the signal travel? It's an infrared wave. After infrared, you move into visible light. With invisible light, there is a range of about 700 nanometers to 30 nanometers, or violet in light. So this is somewhere along the center there, and we call this the portion of the visible light spectrum. So we can actually take white light and use a prism to separate it out into these separate wavelengths. And these are the ones that we can see. Okay, so we can't see radio waves, we can't see infrared, we can't see microwaves, but we can see visible light. All right, sorry about that, guys. I had to step away for a minute. All right, so again, visible light is what we can see. And they make up a very, very small part of the EM spectrum. So one way to remember the separation of visible light is Roy G. Biv: red, orange, yellow, green, blue, and violet. Or sometimes you'll see Biv, indigo, and violet combined there on the end. Okay, so red, orange, yellow, green, blue, indigo, and violet. The next section is what we call ultraviolet. So these are wavelengths that range from 400 to about 10 nanometers. The frequency is pretty high. And that is how you basically get a sunburn. So the frequency of ultraviolet light is high enough that UV rays are able to penetrate and move into living tissue and cells and cause damage. Right? So prolonged exposure to UV light can lead to skin cancer, and that's because essentially the DNA in your cell becomes damaged, and then the cell doesn't replicate properly. They start replicating too much, and they grow into a tumor or a mole or something else on your skin. And so that's kind of how you end up developing skin cancer. It's all because of UV light that penetrates your skin. It has a very high frequency. Other insects can see UV light. So interestingly enough, bees, bats, and some other animals can see it. Humans cannot, but that's how they navigate to flowers. They can use that to kind of figure out where they're going. Now, UV light isn't all horrible. We need it to help us produce vitamin D. So small amounts of UV radiation or UV exposure is important. So you're talking 15 to 20 minutes of sun exposure a day without sunscreen, but anything beyond that can cause damage. And of course, clothing and things like that can block UV rays from hitting your skin. You can also use UV light as a sterilization process. So I know you guys are at home, but some of you were in class with me. And if you remember, whenever we would do science experiments, after we were done, we would put our goggles into the UV cabinet and we would turn it on. And that's basically what happens is that the UV light, there's a bulb in there that emits UV light, and it sterilizes the goggles. So any bacteria or virus particles that might be on those goggles are basically killed by exposure to the UV light. And some hospitals even have these standing UV light emitters that they can put in different hospital rooms to help sanitize that way. All right, x-rays. So I'm sure some of you have had x-rays before, whether from breaking a bone or maybe even from going to the dentist to have your x-rays. And so these have very small wavelengths as well. And obviously they can penetrate into human tissues. Now, prolonged exposure to x-ray is not good. That can cause problems. But it does not move through dense material like bones. And so that's why doctors can use x-rays to look at any broken bones or to find evidence of cavities and things like that. So you can use it to look at solid structures. But prolonged exposure to x-rays is hazardous or dangerous. So what about gamma rays? They carry the most energy and have the shortest wavelength. Very, 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 very small. They do pass through most materials easily. And so you have to have a very thick concrete wall or very thick, dense material to stop gamma rays from moving through. They can be released by nuclear reactions, so from nuclear power plants or nuclear bombs, like the atomic bombs that were used in World War II. There are some elements on Earth that actually emit gamma radiation as they break down, so radioactive material. But gamma rays can be used to shrink tumors as well. So medically, gamma rays can be useful, even though they are considered to be dangerous. So here's just an example of how they can be useful and why they're relevant. And so this is a centigram looking at somebody's lungs. And so they were given a slightly radioactive gas and it kind of showed up on the scan here. And so they were able to see airflow move through the person's lungs. So there are medical implications for the use of gamma rays. All right, so I do want to go back and point one thing out. In the very first slide, so I'm going to go back to the one that talked about radio waves. Radio waves is the largest, but there should have been some mention of microwaves as well. So this is where it kind of mentions here about heating up food, or excuse me, about cooking food. What I want to point out here is that microwaves fall in between radio and infrared. So if you looked at this slide for radio waves and thought, okay, well, I've never cooked food using a radio wave. Well, that is true, you haven't. But what this probably should have said was radio waves and microwaves. So in terms of the EM spectrum, it goes radio waves, then microwave, then infrared. So this particular presentation just combined that. So see right here, there's a little microwave. So microwaves fall in between radio and infrared. And so that's where this cooking food comes from, because we use microwaves to heat and cook food. All right, so that's it for this presentation. It is posted as a PDF. There are some useful links here that would take you to the image or other websites that have more information. So I'm going to stop sharing now, and I'm going to come back to my camera. All right. So your job now is to type in your notes, fill in the blank, make sure that you post them. So today was all about the EM spectrum. So you need to know which ones have the longest wavelength, what they're used for, which one has the highest energy. Remember, there is an inverse relationship. You will have a quiz on this material on Thursday. Tomorrow, we will do a lab where you make observations about exposing particles to different types of electromagnetic waves, and then we will do some review in preparation for the quiz. So if you guys don't have any questions, you're good to go. Make sure you go in, fill in your notes, submit those. If you are missing any work, you must get that done. Some of these assignments that I'm posting, you can use as an alternative for some of the zeros that you guys have. So if you're going to do that, you need to send me a message in school, would you, okay? All right, make sure you finish your test from last Thursday. If you haven't, have a great day. I'll see you guys tomorrow. Bye, everyone.